Welcome to the next in the series of historical reflections with luminaries in our field. This is a special series that we put on as part of the Society for Modeling and Theory in Population Biology. And I'm really pleased to say that James O'Dwyer has agreed to co-host this series with me going forward as we interview several people in the future. And today we're so excited to share our interview with Simon Levin. Welcome to the series, James.
Hi, Sally. Thank you for having me. It's a pleasure to join in and be a part of some of these exciting interviews. I'll start by introducing today's host. I'm sorry, today's guest, not today's host. We're really excited to have Simon Levin joining us. Simon is the James S. McDonnell Distinguished University Professor in Ecology and Evolutionary Biology at Princeton University. And he's had an amazing career and been extremely influential in ecology. He started off in mathematics for his undergrad and PhD and moved to Cornell as a faculty member and then to Princeton in 1992. Along the way, he's had several awards and honors. Sally, maybe you could say a little bit about those.
Yeah, he's a member of the National Academy. He's won the National Medal of Science, MacArthur Award from the Ecological Society of America, Kyoto Prize, so many of the leading awards in ecology and science.
Simon's influence has many different aspects. I would say sometimes people don't always care about numbers of citations, but this is a quantitative biology theory, so maybe we should care about some of the numbers. And in any case, Simon's work has been cited over 120,000 times, and several classic papers each have been cited many thousands of times individually. That shows one aspect of that influence. From my personal perspective, I remember really early on in reading papers in ecology being influenced by the importance of being discrete and spatial by Rick Durrett and Tsai. That was a theoretical population biology paper, extremely heavily cited and influential. And I think beyond those numbers and the specific papers, Simon's really well known for having influenced the development of many trainees. He's mentored, I think, more than 150, maybe getting over 200 graduate students and postdoctoral scholars, which is amazing. And in a way, that connects with my personal experience of interacting with Simon from very early on in terms of working in ecology. I've never been in Simon's lab or been a direct mentee in his group, but I've had several interactions over the years which have influenced me. He was actually the editor for the first paper I published in the field of ecology, and I think he liked it. And that publication process is probably the smoothest I've ever had. So it's been downhill since then. But that initial high impression of my work from Simon hopefully hasn't gone downhill too quickly. But that was an initial interaction which I really appreciated. And then over the years, he's hosted me in his lab group, introduced me to many members of his lab and those people that he has collaborated with, and that's led for me to interactions that still continue today, and also papers that I've co-authored with people that Simon introduced me to. And so that willingness to connect people, to mentor people, even if they're not directly part of his lab, that's just, I think, a signature of how Simon has influenced the field.
Yeah, and riffing off of that, one of the things that really impresses me about Tsai's work is that he integrates so many different things. So it's not just ecology and evolution, but he pays attention to human behavioral influences and how that affects things like the spread of disease or antibiotic misuse. But he also considers things like economics and economic drivers and intertwines that into many of his models that he's done over his lifetime. So I'm really looking forward to learning more about how he integrates all of these aspects and how he's done so over his career. Welcome, Simon. So I'll just start out with a question about when did you first realize that math was a tool that could provide insights into these topics in biology and surrounding areas?
Thanks a lot, Sally. And actually, one of the things you said in your last comments will tell you what's motivated me along the line, because I started as a mathematician because that's what I knew how to do, but I knew I wanted to apply it. And I decided early on I wanted to apply it to biology. Um, I was very interested in environmental problems. It was about that time that um, the work was coming out that Rachel Carson and Paul Ehrlich's work. Paul later became a very close colleague of mine. So I wanted to work on environmental problems. I decided to become an ecologist. Um, but after working in that as a theoretical ecologist for a while, I realized that I really wasn't going to be able to solve those problems unless I began working with economists and other social scientists. So that's continually evolved in what I do. I went to, as an undergraduate and as a graduate student, in mathematics, mainly because I knew that's what I could do, and I could do best. But I was interested in applying that, and initially to biology. I took a biology course uh, at Johns Hopkins when I was an undergraduate. It was not my best course, so much so that I was advised along the way that I was not going to end up being a doctor, which was fine with me. And I also sat in, at least for part of, one of the first biophysics courses anywhere, because Hopkins was one of the places that began that. When I went to graduate school at the University of Maryland, um, even as an undergraduate, in fact, most of my courses, certainly in biology, but even in economics, were not very mathematical. But in
Hmm.
graduate school, one of the young faculty, Rob Kellman, was collaborating and running a course on mathematical applications in um, in biology. So I sat in on that course, and um, I got to listen to some of the real pioneers in the area. And Rob was working in renal physiology. K.S. Cole and Dick Fitzhugh were pioneers in neurophysiology. Nicholas Reshevsky came and talked. He was a pioneer in the field, a controversial pioneer, but he was there. George Weiss was on the faculty and working with Kimura on problems in genetics. So I got an introduction there, and at the same time, I read a lot of the historical work, um, like Locke and Volterra in um, in ecology. And when I completed my graduate work, I told my advisor I really wanted to go on to explore the applications to biology more. And did he have any suggestions? And he suggested I go to work with George Danzig, who was a pioneer in operations research, but was applying a lot of the systems methods in biology. George was a brilliant uh, leader in the development of operations research. I had actually considered going to graduate school in operations research at Hopkins, and I got a fellowship to do that, but I thought that's too new a field. Maybe it won't go anywhere. So I went to graduate school in mathematics instead. I still think that was a good decision. So although I sat in an operations research department at Berkeley, we were working really on problems in physiology, on active transport of sodium across red blood cell membranes, and published one of my first papers in that area. Um, but I got a job offer at Cornell in the math department, and I took it. Uh, and when I got there, I decided what I really wanted to do was to develop my interests in um, in ecology.
Sounds like something that's maybe in common for many people working on mathematics applied in biology, that you found the right course and the right people at the right time that showed what you wanted to do was possible. So just building on that experience a bit, I'm wondering if you could share more generally who the people were that either through your personal interactions or through their research inspired you early in your career to make this connection between mathematics and ecology and biology.
Yeah, so as I mentioned, I went out to Berkeley to do a postdoc. I received an NSF fellowship, one of the early postdoctoral fellowships, and went out to work with George Danzig, who was a leader in operations research, but who had turned some of his attention to applying the systems theory kinds of approaches that he pioneered to problems in biology. And George was a huge influence on me because he basically showed me, both from the way he treated me and also in what he was working on, that one should work on whatever one was passionate about. Didn't matter what your background was, but you could turn what you knew to good use by whatever you wanted to work on. So George worked on designing cities. He was interested in the blood flow problems. He was interested in optimization problems in operations research. He was interested in traffic flow, et cetera, et cetera, et cetera. And so it was a huge influence on me because it inspired me to feel that I didn't have to work in some narrow lane in my research, but I could feel free to reach out and work on whatever I wanted. When I got to Cornell, I also had a senior mentor named Henry David Block. We called him Dave. And Dave had been a pure mathematician, purer than I was, and had switched into sort of biology, really artificial intelligence, but he was interested in the brain as well. And I said, David, how did you do that? And we also collaborated on some things together. And he said, well, I woke up one morning and found myself in the middle of a locally compact Hausdorff space. And I thought, that's no place for a grown man to be. So it was also inspirational for me to see that he had committed himself and made that transformation. In terms of interpersonal relationships, two other people who were very influential on me, even though neither one of them was at all mathematical, were my colleague at Cornell, Dick Root, who was an excellent ecologist. And when we began to talk, because I sat in on his course, we became friendly, and he really encouraged me, and he said, we need somebody like you in the ecology department. Very few ecology departments at that time had anybody who was very mathematical. Nobody who was, that I know of, who had a PhD in mathematics. There were several of us starting out at about the same time on that. For example, Bob May shortly thereafter, and Mark Feldman more on the genetics and evolution side, and Joel Cohn. But this was unusual. So Dick was a big influence, and he introduced me to Bob Payne. Bob came and gave a lecture at Cornell. By then, I had moved partially into the ecology department, and I was inspired by Bob's talk. Not at all mathematical, but clearly something that could use mathematical thinking. And he invited me to come out on sabbatical. I had a sabbatical coming up a year or two later. And that was an extremely influential and important interaction for me. Because although Bob wasn't mathematical, he thought about things in a way that were familiar to mathematicians. He, in terms of the structure of the system, the emergence of macroscopic properties from microscopic interactions, and so he didn't talk in those terms. In my equations, he referred to as flute music, but it was a wonderful collaboration. In terms of
so what does flute music there mean, Simon? Just something that's
well, anything, if you look at flute music, it's a bunch of bars and little symbols, and they're not, when you're playing music, they're not the same kind of symbols as when you're doing mathematics, but there's somebody who does neither. And Bob was neither a mathematician nor a musician, They just look like some foreign language to him. In terms of people whose work I read that was influential, I would single it out on the. Of course, I read the classic things of Haldane, Fisher, and Wright. In fact, I even got to meet and talk to Sewell Wright, which was inspiring. But I would say on the genetics and evolution side, my colleague Bruce Wallace at Cornell, and with whom I taught several courses together, and Dick Lewontin's writings found the middle ground. They deep into the biology, but phrasing questions in ways that were ready made for mathematicians, and the legacy of Jevelyn Hutchinson, and especially his students Bob MacArthur and Larry Slobodkin. Slobodkin was a personal friend. I mean, I got to meet all those people and talk to them, but Slobodkin I knew very well. And they all explored conceptual issues, not necessarily in mathematical terms. MacArthur probably the most mathematical. And Hutchinson especially, and to some extent MacArthur and certainly Slobodkin, were elegant writers. I had to relearn how to write papers when I realized that this sort of stilted, because I had been a newspaper contributor and similar things, and a decent writer early on, but writing math papers is not like that. And I had to relearn to write. I wanted to write, especially like Hutchinson wrote. And then later in my career, and two people who were extremely models for me and influential were Paul Ehrlich, with whom I continue to be close and collaborate, and the economist Kenneth Arrow, who was also a collaborator of mine. And Ken was another. Ken, by the way, was a colleague of Danzig's. He thought it was a shame that Danzig never won the Nobel Prize. He helped to bring him from Berkeley to Stanford. And in speaking to him about an area he knew nothing about, he said, I'm certainly very interested in that because I know nothing about it. So it was a great opportunity for him to learn. The nicest thing I ever heard anybody say about Arrow, and there are a lot of nice things, is at his 80th birthday party said, the thing about most notable about Ken Arrow is he never stopped being a graduate student. And so I thought that should be a goal, something to aspire to always have the excitement of being a graduate student and learning new fields. So that explains to some extent my eagerness to move into new areas, because you're on the steep part of the learning curve and there's still so much to learn there.
You know, it's so interesting that you mention operations research, because it's an area that brings together, it knits together a lot of these different approaches, but it's not a commonly unknown field or major anymore.
Well, it is here. We have a Department of Operations Research and Financial Engineering. A lot of the best, for example, game theory courses and game theory work are done in the Operations Research Department. I often borrow methods or perspectives from operations research theory, like optimization and search theory and game theory. I was an undergraduate at Hopkins and had one of the first operations research departments anywhere. And I mentioned, I don't know whether it was caught before, that I had the opportunity to go to graduate school there. In fact, I was offered a fellowship to go there and only a teaching assistantship at the University of Maryland. But I was worried that the field was too new there and wouldn't.
Well, I guess I should be clear that it's not known to scientists, and yet many of the questions and approaches are of value in science.
Absolutely.
Yeah. All of us working in theory love those moments that are aha moments, where something that was puzzling or unknown to us all of a sudden becomes clear. Do you have a favorite one from your career?
There are a number of them that I could identify there. I'm always have learned the most from rather simple models, toy models that strip away a lot of the details and still give rise to interesting insights and maybe starting points, things that are wrong. At least they're wrong under most conditions, like Fisher's fundamental theorem of natural selection. That's still a model I teach my class. I show them the conditions under which the mean fitness of a population is maximized. And then I immediately tell them, but look, this is not what happens. And here are all the reasons why it doesn't happen. Here's the list of assumptions that are needed, random mating, et cetera. But most notably, the fact that the fitness landscape is constant. And it's a takeoff point, but it helps me to think about what what we need to put into models, why it doesn't break down, and to start thinking about frequency dependence and coevolution and the need for game theoretic models. Another example of that would be theories of competitive exclusion, models of ecological succession. I didn't know anything about succession until I started going to national parks and the rangers would talk about succession. I thought, I never thought about that. That's a wonderful concept. And so it really, that simple organizing theme clarified things for me. My approach to problems is always to go back and forth between the general and the specific. I'm trying to look at particular case studies, but take a step back and try to abstract what is general in the picture, and that, and to ask what details can I ignore, and the more I get away, the more I understand. It also explains why I like to work across fields, because I'd like to see the similar features that go on. And for me, James mentioned my paper on scale and pattern, and so thinking about pattern and scale was really probably the most aha moment for me, and understanding two things. One is that optimization approaches weren't going to get me there, and I had to do game theoretic approaches. I remember beginning work with Danny Cohen, the Israeli botanist, and my student at the time, Alan Hastings, who's now member of the National Academy of Sciences and already retired, but this was a long time ago. When we started with optimization approaches and realized this is wrong, this is not what's going on, we were thinking about the dispersal, and that was clearly a game theoretic problem where lots depended on what others were doing, but also thinking about the relationship between phenomena on multiple scales and how the patterns we see at the broader, it's a lot like what I said before about abstracting back from case studies, but that if it, you know, if you take, if for example, well, something like chaos in which it's impossible to predict exactly trajectories, if one takes a step back and averages over or introduces some noise, one gets statistical predictability. The probability distribution becomes so. The ability to take a step back and look at what emerges when you coarse grain the system, I'll say, it is something that has led to lots of aha moments for me.
I think that's great advice. And yeah, the zooming out, it's so easy to get kind of stuck in the weeds of a project, but you don't really get it until you're able to zoom out. James, over to you.
So the pattern and scale paper, that is pretty well known, I would say. So I'm wondering, is there a paper that's maybe a favorite of yours that you wish was better known? Is there something that you particularly like about a paper that you want to share with us?
Yeah, that's a fascinating question, because you told me you were going to ask that. So I went back and looked, and I thought, well, this paper, I was thinking about my 1974 paper on dispersion and spatial ecology, and I thought I'd learned a lot from that paper, and I wondered, but then I looked it up and it had about 1,500 citations. So I said, I can't claim that that's a neglected paper. So I went through a number of others like that, but eventually I thought that there's there are two papers I did with Paul Ehrlich, one with Paul Ehrlich and Ken Arrow. With Paul Ehrlich, there's a paper somewhere around 2005, I think, which looks at the evolution of social norms. And because Paul and I at about the same time became interested in social norms and how important they were for governance and how they arose and what made them stick. I don't think I don't think that paper is undercited, but I'm not sure how many people are aware of that work, because thinking about social norms has become more the thing now. But there's one paper that Paul and I wrote with Ken Arrow just before he died, which is called Some Perspectives on Linked Ecosystems and Socioeconomic Systems. And for us, that was a really important paper. Ken had pointed out to me that it's no accident that ecology and economics start with the same three letters, eco, which means a house or something, and therefore that the problems that were faced in ecology and the problems that were faced in economics were very similar. In fact, that economic systems were ecological systems, that ecological systems are economic systems, and more than that, that they are both not only complex adaptive systems, but they're linked together into a larger complex adaptive systems. And was very happy with the paper that we wrote, which brought together the perspectives of an economist, a population biologist, and more of a community and ecosystem person, namely me. But it was published in a book in honor of our colleague Partha Dasgupta, a great economist. And I saw it's only been cited 31 times. So I thought, okay, that's the one I wish people knew more about, because I really, I began my career as a mathematician because that's what I knew how to do. I turned to biology because I was interested in that. I quickly turned to ecology because I really wanted to make a difference. And then I realized that I couldn't do anything just being an ecologist. I had to reach out to work with economists and other social scientists. And I couldn't have done better than Ken Arrow, and who was a Nobel laureate in economics. And so the ability to blend our different perspectives was a lot of fun, and also I think has some messages that I'd like people to hear.
Simon, how did that collaboration come about? Did you already know? You knew Paul from a long way back, but did you already know Kenneth Arrow?
So I knew Ken Arrow a little bit, probably better than he knew me, because we had been on a panel together on the National Acid Precipitation program and evaluating it, together with a number of other distinguished people like John Tukey, who was on that, the great statistician. And I had actually heard Arrow lectures when I was much younger. But in 1992, I think, or three, I got invited to, because I started working at the Interface with Economics, to join the board of an organization called the Bayer Institute of Ecological Economics, which is part of the Swedish Academy of Sciences. And that was one of the most influential things I did. Going to the Santa Fe Institute was at about the same time, and also influential. And Ken wasn't actually on the board, but every year, and I've been involved with the Bayer Institute for the last 30 some years. And we would go out and to an island called Asco, mostly. Sometimes we went somewhere else. Choose a topic and write a paper together. And we did that. Ken and Paul and I did that almost every year. Sometimes one of them Ken didn't get to because he got as far as Chicago, and they said your passport is not up to date, so he had to go home there. And one of the papers that you mentioned early on, James, was a paper in which Arrow was the first author, the one on carrying capacity in the environment.
Yeah.
And we got to know each other the whole group of us. There were about a half a dozen of us. Partha Dasgupta was another one, Karl-Johan Mailer, and a number of others whom you know who would come off and on. But there were about a half a dozen of us who went every year, with only a few exceptions, for almost 30 years. Until I think Ken went until the year before he passed away, and then Paul and I went until a few years ago. And we'd write a paper every year, but the real benefit was the ability to get to know each other and to work together.
Mm-hmm.
So, as an example of that, and this will tell you a lot about Ken Arrow, and the way I mentioned before that the nicest compliment I heard to him is that Ken Arrow never stopped being a graduate student. I asked him a question at one of our excursions out to ASCO. I was interested in life history theory, and economists are interested in something called dynasty theory, which is involves how much you leave to your children. And you can see the superficial similarity between the two of them. In all cases, you have limited resources. You have to decide, do I consume them now? Do I save them? Do I save them either for my old age or to give to my children? In life history theory, it's not money you're saving, but you can decide to invest in yourself, invest in your children, etc. And like I said, Ken, in dynasty theory, one often simply takes your children as an extension of yourself, and therefore you live forever. But that sort of implies that you're replaced by one individual. And although it's true that in a stable population, everybody is replaced by one individual on the average, there's some variation. And does that variation alter the uncertainty, alter the predictions that you would make from dynasty theory? And he said, no, it doesn't. He did think for about 12 seconds before telling me that. And then I took that as gospel, and then we continued going back to ASCO year after year. And 4 years later, he came up to me and he said, Simon, 4 years ago, you asked me this question about dynasty theory, and I gave you an answer. He said, I've been thinking about it. I gave you the wrong answer. He said, and he explained to me why. And so we began working on it. And we wrote a paper. It was published in PNAS, which borrowed from life history theory and borrowed from dynasty theory and dynamic programming, Richard Bellman's work, in order to compute what should be done. I'm continuing to work on that because although we didn't set out to do this, one of the implications of it was if you identify what would be optimal, or and we weren't even working in the game theoretic sense yet, then as to what you should leave for your children in terms of wealth, that's going to affect what the wealth distribution is going to be in the population. And we made predictions about the wealth distribution in the population and why it was continuing to the inequity was continuing to increase, which was something of great interest to Ken. And we weren't quite right. We knew we weren't quite right because we were getting power laws. We're getting something, that looked like log normal on a distributional scale with a variance that was increasing over time. But we knew that the data showed that the right-hand side, the rich end of the spectrum, was should have been more like a power law, should have been more spread out, the fatter tail. So I've had two students continuing to work on that, and until Ken died, we worked with him on it. So anyway, that's a long answer to your question as to how the collaboration developed. The beauty of the Bayer Institute, and I think this probably will relate to one of your later questions, was it brought together people from very different backgrounds and disciplines and taught them how to work together and how to learn to trust each other and to learn the others' discipline. So it was a wonderful experience, and I continue to benefit from it.
That's a remarkable story, and I suspect that this might come into the next question. Do you have advice for students entering into the field, and insights about how you approached theory and collaboration that you'd like to impart?
Yeah, I can give 3 pieces of advice on that. The first thing is the lesson I learned from George Danzig, which is find what you're passionate in and just do it. And when I was still a postdoc at Berkeley, I had been in conversation with the chair of the math department about staying around there as an instructor for a while. But I got this job offer at Cornell in the math department, and I took it. So I went in to talk to him, and I said, I'm going to be leaving because I got an offer in the math department at Cornell and go there. And he said, "Oh, good, you're very lucky." Well, I said, "What do you mean lucky?" He said, "Well, when I was your age, I couldn't have gotten away with what you did." I said, "What did I do?" He said, "You took a year off." I said, "No, I was working really hard." He said, "But yeah, but you weren't doing mathematics." And
Mm.
I thought, so that just inspired me, not in the way he intended. He said, "No, if I want to do something good, I've got to do what it is I'm passionate about doing." The second piece of advice I would have is if you want to move from more mathematical areas into biology, um, pay attention both to the empirical side, to the data, and also to the people who you want to be your audience. One of my colleagues who was at a bifurcation point of that sort some years ago asked me, should I go into a math department or into a biology department? I said, if you're serious about what you're doing, if you want to do serious work, you have to go into a biology department, because otherwise you'll twist what you do in order to impress your mathematics colleagues. If you really want to have an impact, it's the biologist you should be talking to, and you want to impress them with what you're saying, not the methods that you're doing. So that was the second piece of advice. And the third piece of advice, and I do this in my class too, is you're going to have to collaborate. You're not going to be expert in everything. So learn how to choose people you like to work with, and I've been fortunate to have a lot of them along the way, and whom you trust, who you can rely on, and who want to listen to you as well as telling you what to do. And all of my most interesting, most useful collaborations have been with people who wanted to learn from me as much as I wanted to learn from them, and in that way, we um, we all benefited.
Right, right.
Great.
Yes.
So I'm going to maybe go back to some of your comments earlier on when you were talking about Cornell and the ecology department there. My perception has been that within biology, ecology is historically a really, maybe welcoming is the wrong word, but a field that's very open to mathematical modeling and goes back a long way in ecology. Sally might say evolutionary biology is even
Yeah.
more so. I don't know. She might disagree with me on that. But just thinking about the fields you've worked in and how things have changed over time, would you say the perception of modeling and theory in ecology and the other areas you've worked in, has it changed since you started out?
Dramatically. And let me back up a little bit on to answer that. When I started working in these areas 60 years ago, there was essentially almost no mathematics that was making its way into biology departments. I think the closest to an exception would have been in evolutionary biology and population genetics, where certainly, and I mentioned Dick Lewontin before, and of course, Fisher and Wright and Haldane were quite mathematical. A lot of it had to do with especially plant and animal breeding that this was developed.
Mm-hmm.
This was, I would say, before ecology, before it really took off. I mean, Lotko and Volterra, a little more than a century ago, certainly developed approaches applicable to ecology, and their equations were taught in ecology courses, but mathematical modelers were suspect then. Today, and there were very few of us who were working in this area, even when I got started. I mentioned Bob May, Joel Cohn, and Mark Feldman as examples. And then, of course, there were others like Sam Carlin, but they were operating out of math departments. Today, I can't imagine a really first-rate biology department without a lot of people who are doing these sorts of things. A first-rate ecology department without at least one or two people who are doing things from a strong mathematics background. Biophysics and genomics, and so in those areas, I would say what was almost empty back then has become mainstream and absolutely essential. That's also true to some extent, I'd say, in neurobiology. There are a couple areas where it ought to be have a stronger influence where it doesn't yet. One of them, the one area I should have mentioned where it does have a strong influence is the dynamics of infectious diseases and epidemiology. That's another area that goes back more than a century to Ronald Ross's early models of malaria. But now there's, of course, we saw this during COVID. There are a lot of people doing various kinds of mathematical models, some analytical and some based on agent-based models and computer modeling and machine learning, et cetera. The one area where I think mathematics has a lot to contribute that still, to my perception, has not received its due credit is in immunology, where I would particularly single out work such as Alan Perelson's on the mathematics of the immune system, many aspects of which have similarities to ecological systems. But without questionably, I think modelers and theoreticians are much better accepted today, at least in the leading departments, than they were 50 or 60 years ago when it was a real slug.
Yeah, even when I started, I remember there was an atmosphere of, oh, they're just armchair theoreticians. And so that's advice that you gave earlier, Simon, about how you have to engage with biologists, with their data and their questions if you want to have an impact. I think it's people like Simon doing that over his career that's really changed the perception of theoreticians and what we can do.
Yeah, actually, Sally, it reminds me of a paper I read once. I wish I could find this, by Mark Kutz, who was at KAC, who was a very famous mathematical physicist. And he said that mathematical physics really took off and became a discipline when the mathematicians who worked in that area became physicists. So going back to your question before, Sally, I would say I should have listed this under the advice to modelers. If you want to make an impact as a mathematician in biology, become a biologist. So that's why my first sabbatical, I went out to work with Bob Payne to find out what field work was all about. And you want to get to the point where it's not just where you sit in your office and expect people to come in with problems and ask you for help. That'll happen, but it's not very exciting. You want to be involved with the interesting part of the contribution of mathematics, I think, is not in solving the equations, but it's in helping to decide what the equation should be, namely, how do you describe the system? What's interesting about this system? And that's you've got to become a biologist. You've got to be asking the questions and telling the field biologist and the lab biologist what it is, and you shouldn't be telling them that this is an exchange operation. Sometimes it works like this. When I went to buy my future wife her first gift, it was I decided I was going to buy her a purse, and my mother said, "I'll come along with you because you don't know what you're doing." And we went into the store, and I picked out one that I liked, and I pointed to it, and she said no. And I picked out another one, and she said no. And I picked out a third one, and she said yes. And so I felt I had picked it out, but it was a collaborative process. And when Bob Payne and I started working together, we began by my going out into the field, learning the taxonomy, and then learning the dynamics. And then I proposed a model to him, and he said no. And I proposed another model, and he said no. And the third model, he said that one I like. And we went back and forth, and we iterated the model in that way. And it was a true collaborative enterprise where I was suggesting things, and I had become a biologist, but a different kind of biologist than Bob. But it led to a good interaction.
When you're embarking on a topic kind of outside of your expertise, is there something that sparks your interest, that makes you think, oh, there is something here I can tell, and kind of motivates the models that you do?
Well, there's two things that drive me, and I'm a little bit schizophrenic about this. In fact, you can see if you look in my publications that sometimes there might be an application with no mathematics, and sometimes it'll be mathematics with no application. Both parts of it still appeal to me. So I'm interested in a problem if its solution is important and makes a difference. But I'm also really driven by being able to see the similarity in the sorts of questions that arise in different systems. That's what drove me to sort of be working in complex adaptive systems, which, for those who don't know, are systems that are made up of lots of individual agents that interact with each other, and from those properties, there's the emergence of more macroscopic features. In all those cases, there is the need to scale and from the microscopic to the macroscopic, just like one does in economics. There are scaling laws that develop. There is a statistical mechanics that has to be developed. There are problems of pattern formation. There are questions about the robustness of the patterns. And for many of those systems, maybe not so much some of the physical systems, there's the fascinating question, which is, I think, at the core of trying to do anything about environmental problems, of conflict between the interest of the individual and the interest of the collective. So in evolutionary theory, this is manifest in things like the selfish gene, up to what's good for the organism, up to approaches of group selection, and when that might be relevant, and why that's not always or often even a good idea. But so a lot of the problems I work on now share this feature of being features in which individuals have one agenda, and there's a social optimum, and they may not be getting there. And the questions we ask, whether it's in socioeconomic systems or whether it's for slime molds or bacterial biofilms, is what would the social optimum be? What would a game theoretic model tell you about what's really going to happen? Is there what an economist would call a second best solution? In other words, a compromise solution of some sort. When you're dealing with an environmental problem, that's an important question to ask. But the same thing one can ask in the evolution of cooperative behavior in bird flocks, fish schools, etc. So I see these commonalities, and not for one thing, it allows me to borrow from what I know about one sort of system and say, hey, everything we developed here, we can carry over. The equations might be different, but we can think about the system in the same way. So almost everything I've worked on is work of that kind, where one has to ask about emergence, about coarse graining, and how to understand the macroscopic problems in terms of the microscopic, what details are important and what details can be ignored. And most recently, how are the conflicts between the interests of units at different levels resolved? And that just, and many of those questions even occur in physics systems, except for probably what the best interest of the individuals are, et cetera. But in economic systems and even in how we behave during epidemics and in ecological systems, those questions come up over and over again. What's the conflict between individual interest and the collective interest? How are those resolved? What can we learn? For example, a lot of what I do now is, and that includes, by the way, I've been consulting for the Boston Consulting Group for 13 years, which is interested in what can we learn from evolutionary theory that would guide how businesses ought to operate.
Interesting.
But simple ideas like the trade-off between exploration and exploitation, the role, and how does that come about in evolutionary biology? Natural selection winnows diversity, but the environment changes, and so you need mechanisms to reinfuse the diversity in the system, and that's mutation and sexual recombination, et cetera. And those have evolved, and that's the same as the trade-off. For me, it's the same as the trade-off between exploration and exploitation. And universities, institutions, businesses have to reach that balance between exploiting the fields that they know are working well and being able to catalyze new fields. And the trade-off between them is going to depend upon the environmental characteristics they're facing, and it's going to be a function of scale, et cetera, et cetera. So I just am fascinated when exactly the same considerations come up over and over again.
And you mentioned conflict, but also tension. It's probably when you see a tension or maybe don't know what will result from the model that.
Absolutely.
What
The push and the pull, the yin and the yang.
Thank you.
So last question, although I'm sure we can probably keep going for as long as we wanted to. Last question I've got written down here. And so I don't want to give too much of a generalization in this setup for the question, but you've mentioned Lotka-Volterra equations a couple of times, that those might have been taught in ecology classes in, say, the 60s and 70s, and probably still are now.
Absolutely. I will teach them in a week or two.
Right, there you go. And so, there's other areas of mathematics and computational methods, simulations of various kinds, or numerical methods to solve equations. Those are toolkit of theoretical ecologists, but I think they would all be sort of recognizable, more or less, to somebody who was training in at least in applied mathematics applied to ecology when you were. But I'm wondering, what we've seen in terms of machine learning and statistical methods in the last few years, maybe a focus more on prediction, or even grander claims about artificial intelligence and its role in science. Do you think that the tools of the future will be recognizable to people now, or will they be very different?
All right, so let me answer that question in a couple different ways. First of all, one has to realize, and I know you do, that models are not all for the same purpose. You mentioned prediction. That's one sort of model, but we also use models for understanding what's happened in the past. Those are very different demands for validation. We also use them for control. uh, management of a fishery or something, and for that we ask different, or we may just use it as, for example, a flight simulator to give someone a chance to play with the model, or just to visualize what's there. In terms of the methods changing, as you already mentioned, that's not even a hypothetical. The field has already changed. Give you an example. I took a course in numerical analysis in graduate school. It was about how do you write approximations for running on a computer. Nobody in the class, including the instructor, went anywhere near a computer back then. This was a long time ago.
Yeah.
Indeed, the methods are expanding, not replacing what's there, but expanding on what was there. We recently ran a meeting on artificial intelligence and machine methods, and we had some distinguished mathematicians at the meeting. And I asked them, I said, are you threatened? Because computers are great now at proving theorems, and you can prove a lot of things that mathematicians haven't been able to prove. Are you worried about being replacing? And they said, no, it's great because it frees us up to do the things that computers aren't good at, which is asking questions. The computers apparently in mathematics and are not very good in thinking about what's the next question to ask. So they become complementary tools. Simple models are still going to be essential, but agent-based models, computer simulation. When I started my career, I looked down on computer simulations, but until I realized that they were just a data generation tool to begin to explore relationships and things of that sort. Nobody in the math department when I was there at Cornell had a computer back then. Now I imagine everybody does, and that a lot of them, no matter the field, are using them to look at cases. And when you look at lots of different cases, it suggests patterns and relationships. So I think agent-based methods, network methods, machine learning methods, data-driven methods are obviously becoming increasingly important. And yeah, the field won't be recognizable in that sense 10 or 20 years from now. But people working in the field have to evolve with it. Doesn't mean you have to switch over and do those things. That's where the collaboration comes in. You have to recognize that those things are important, learn to what degree they to be. But I still think that when all is said and done, the ability to derive new ideas, is going to result in looking at all these things and saying, what do we learn from this? What's common to all these things? What's general? And why? I'm sort of biased that even when I prove something mathematical, if it takes 6 pages, I feel like I've missed something. That there are some simple underlying principles that are responsible for what's going on. And now I've got all these data, whether it's from the field work or from data that some data intensive methods have brought out, is how do we abstract from this? What do we learn from this? Can we develop simple models to help us to understand what's really going on? Not all organisms evolved to deal with environmental changes. They don't have computers. They evolve strategies. That's what we're trying to understand. So ultimately, I mean, that's one of the things we're trying to understand is how does the brain work? How do organisms parse through the information, all the information they get, and how do they simplify? Goes back another person I didn't mention whose writing has been very influential to me is another Nobel laureate in economics, Herbert Simon. And Simon is probably best known for developing ideas about what are called bounded rationality, and based on the notion that are both there are cognitive limits on what we can do, and also we're dealing with decisions that have to be made on shorter timescales, and that therefore we need to develop heuristics and simple rules of thumb. And so that I think the field will have changed. You've got to be able to take advantage of these methods, but the old methods will still be central in helping to understand why we're getting these patterns.
Simon, thank you so much for taking this time with us. I have to say, it seems like not just Kenneth Arrow, but you yourself have managed to have that kind of graduate student attitude and a sense of discovery for your entire career, except that you're a very clear thinker, much more so than I was when I was a graduate student. So thank you for doing it.
I figured if Kenneth Arrow can do it, I can try to do it. And I still take graduate students and postdocs, and it's because of what I learned from them. They always, it goes back to the last question about new methods. They know the new methods, and they take me with them there
Right.
and force me to keep thinking. So thank you very much.
Thank you, Simon.
Thank you.